Last time we uh, got some basics of Rham theory. Let's review a couple fundamental concepts. Today we're gonna fill in some of those basics in detail. Last time we, and then next time we'll finally get to degree, Gauss integral, and maybe Whitehead integral. So great. So let's recap some key concepts. So forms are really just are multilinear, also alternating quantities to integrate. And we had lots of examples last time. Let me start with a non-example. You can build on forms, but arc length would, for example, be the integral of square root of dx squared plus dy squared or something like that over a curve. So that's obviously not linear, despite what college algebra students might say by simplifying. And then they encode and generalize vector calculus. So for example, in R2, you can take a function and take its gradient, and you get a vector field. You can also, I'll call it del cross, take the difference of mixed partials in a vector field, and you get a function back. And functions are just zero forms. So they're a way to take no tangent vectors at every point and spit out a number at each point, which is sort of smooth as you move around. Well, that's just a number at each point, which is smooth. That's a function. And vector fields can then be made into one forms using the dot product, the inner product. And functions also give you two forms, because you can take this standard notion of area everywhere, dx wedge dy, and just sort of stick a function from it, and that's sort of a density function. So at the highest dimension, you want to think of it as a density function, and then basically they're always density functions, except that there's the question of density in which direction, and forms are this structure that lets us talk about densities in directions. And then we have, in this case, we have Green's theorem. That says that if the boundary of some region is a curve, then the integral over that curve of a vector field is equal to the integral over the region of this sort of del cross on the vector field. And that's a function now that we can integrate over the region. And what this generalizes to is the generalized Stokes theorem, which says that the integral over the boundary of some manifold, so a region in the plane is an example of a manifold of some form, is equal to the integral over the whole manifold of D of that form. And we'll be using that a lot. And what I wanted to then give you a sense for how these ideas are really so basic to both the development of fields, especially electromagnetic fields, and topology. So here's a basic question. So some sort of, let's talk about a basic example in both in field theory and topology. So a basic question is, when does a vector field have a potential? Because then we can just evaluate it over a curve by just taking the values of the potential function at the endpoints. Well, because let's remember that this del operator is just taking mixed partials of your function. Then when I take del cross, we have, so a necessary condition is that del cross of the vector field must be 0 for it to have a potential. Looking up here, we have del composed with del cross is 0. So if I'm going to be in the image of del, that means I must go to 0 under del cross. And a key property that we're going to see later, by the way, is that this way to exterior differential of forms always squares to 0. That's a remarkable property that we'll be using quite a bit. So that's a necessary condition. Is this sufficient? And I think we talked about this a bit, but the answer is it depends. The topology of the region of definition. For the vector field. So, for example, our d theta last time does have and if we translate it to a vector field, we could take its del cross, but I'll just say does have d theta equals 0. Again, that's going to hold in general for things which are d. This d theta is maybe a little bit of an abuse, but not too much of one. We talked about that last time. So, but it doesn't have you can't really call it really df for any function. And let me emphasize well-defined function, because theta is sort of a multiply defined function. Since by Green's theorem, if I integrate around the unit circle, and remember theta is defined in R2 minus 0, integral over C would be 0 if there's a potential function, because you just would be taking then the integral around C would be the value at one end of the curve and the other end of the curve, but the two ends coincide, so the difference is 0. But of course, the integral over this C of d theta is 2 pi, and that's not 0. Another example, by the way, we could look at d theta sort of centered at the point P. So P is just some point in the plane, and I could be taking the angle around that. So exercise, go back to the definition of d theta, write it down what d theta sub P is. This is easy. You're just going to do some x minus a's and y minus b's if P is the point A, B. And I can also take the sum of those, right? And now there's going to be lots of different curves that, I could go around one, but I could also sort of go around one and the other and the other. And it becomes this interesting question. It's like contour integration over the complex numbers where you're picking up residues. It's a very closely related example to that. And so it can be tricky to keep track of all that, but there's a key theorem that over any region R in R2, if I take the I'll go back to vector field, the curl-free vector fields. And within those, I've got the conservative ones. So again, if you're conservative, you are curl-free, but not conversely. And both of these are sort of infinite dimensional. But this quotient is finite dimensional. Or sorry, well, it depends on the topology of the region. So let me say it this way, is a vector space dual to the holes in R. And really what it is or dual to the curves in R modulo an equivalence called homology. And what you do is there's really a pairing for this duality, is that you take a curl-free vector field and a curve, a closed curve, these are closed, and you just see, and you just take the contour integral over C of the vector field. So there's some duality between these curves and the vector fields or one forms. Just for later, I'll say notation. These are the first cycles in de Rham theory in the region, and these are the first boundaries in de Rham theory in the region. That's notation. We probably won't rely on it too heavily, but so you've got this this idea that the defect of the difference between being curl-free and being conservative is exactly governed by the topology, or you could look at it as a measure of the topology, or sort of more democratically, the basic object is a pairing. Whether I'm more interested in curves to begin with or vector fields to begin with, I'm going to be agnostic. I'm just going to say there's a way to take a vector field and a curve and make a number. And this passes to, this becomes a perfect pairing. When you take curl-free vector fields modulo the conservative ones, in other words, the conservative ones will have will pair to 0 on everything, and something called homology of curves. So calculus and topology end up being dual. So yeah. And you see that then the topology of the region would tell us, if we want to think of this d theta sub p as some kind of magnetic charge at the point P that's causing this way to go around. And if you look at the formula, by the way, it blows up at P. You have to have that in order for the integral around a large curve or a small curve to be the same. But you then can, for example, count the number of anomalies inside by integrating over a large curve around everybody. So, so once again, topologists care about how many holes are being introduced in the space, and physicists might be interested in understanding the same integral for the number of charges inside. Okay. So before setting up Rham theory a little bit better, which is again our main goal today, I wanted to talk a little bit about topology, in particular topology of manifolds, because as we see here, this distinction between is the form defined on all R or a subset is important. It's important once we start thinking about the underlying calculus that goes on, and you know, at the risk of introducing a topic, you know, the study of manifolds that is deserving of a course in its own right, let me just say a little bit more. So manifolds are really locally Euclidean. And so that means that, for example, if I'm on some surface, and it doesn't even have to be compact, let me give you a first example. There can be this, this can go forever. That's a pretty, but if I lived on such an object, if you were a little ant living on this surface, it would feel flat, just as it feels flat for us on the Earth, even though the Earth is a sphere. And basically a manifold is any object all of whose local residents see it as Euclidean. So for example, the letter X is not a manifold because if you live at that crossroads, that doesn't seem like a one-dimensional Euclidean space. You've got your choices. So what are the flavors we're going to be looking at? So for us, generally, mostly subspaces, but not entirely. So I wanted to talk about different kinds of manifolds. So we've already implicitly talked about a fair amount of codimension 0 submanifolds of Euclidean space. And that's just Rn minus some sets so that everybody has an open ball around it that's contained in the set. That means that you would be locally Euclidean. You could even, for example, take R2 and look at the complement of a Sierpinski triangle. And that will be a codimension 0 submanifold. For us, it's going to be more like R2 minus a collection of isolated points. We talked about that just now. R3 minus the coordinate axes. That's kind of an interesting manifold, R3 minus the coordinate axes. And the point is that in this case, de Rham theory is sort of easy to develop. So it's basically as we do it for Rn itself. Okay. A second kind of manifold that we're maybe going to talk about here and there is, well, positive codimension. So, for example, Sn sits as unit vectors inside Rn plus 1. Or I could look at a torus inside R3, right? And we could always use ambient in from Rn plus 1 or Rn or whatever differential forms. But the thing to note there is that those are not going to be efficient. So let's do an example, give you a quick example. If I look at S2 inside of R3, and I take the one form, omega equals x dx plus y dy plus z dz, then around along any curve, because that's, we want to integrate that along, say, some curve in S2. Its tangent vectors, well, are going to be tangent. They're tangent to the curve, so tangent to S2 as well. And exercise then any tangent vector to S2 would, and thus C would be evaluated to 0 by this omega. So what you could do is formally say that omega is set to 0, and you could work with forms, sort of knowing that we're systematically ignoring the ones that always integrate to 0. That would work okay. What you eventually want to do is have some more intrinsic definitions that don't involve the ambient manifold at all, that really sort of only use the local Euclidean structure. That is part of what a good systematic non-crash course development of Rham theory does, but we aren't going to. Okay, and let me finally talk a little bit about, so the third kind of manifold that can arise are, I'll just call them quotient constructions. So the key is that a smooth function, let's consider a smooth function on the interval, I is what I like to call the interval 0, 1, such that any derivative at 0 agrees with the same derivative at 1, including the 0th derivative. So the values are the same, the first and second derivatives. I claim that those are the same set of objects as the smooth functions on the circle. Maybe I think of this inside of R2, or again, you could take whatever circle wherever it occurs and think about its functions. And then you could do this with forms. And then the good old dx from single variable calculus corresponds to d theta under this. And again, I'm not going through the detail of how you do this with forms, but it can be done. Similarly, if I work on a square and have functions so that the whatever partials at the left-hand side are the same as the partials at the right-hand side, and similarly for the top and bottom of the square, those kinds of functions, those periodic functions, and again, it's with periodic derivatives of all orders, are the same as the smooth functions on the torus. So left and right become the same. It looks like a cylinder. Top and bottom become the same, and you get a torus. So you can often think in terms of, if you've got these relationships between these manifolds, if they're smooth identifications, you could actually deal with smooth forms. It's much trickier, and I don't recommend it. To think about if I take a 2-disk and I take every point on the 2-disk, then I get a 2-sphere. Okay, that's fine. But the smooth structure, the functions, etc., are a lot trickier because, a curve going through this, in order to understand sort of where I come out, I would be sort of going in one side. And to understand where I come out, I need a lot more data than where I entered the boundary. So it really depends on maybe your tangent vector and higher order information. So we tend not to deal with that. We tend to use other local coordinates and things like that. But I just wanted to make note of these quotient constructions because sometimes they do arise also with structures at infinity. Okay, so let's finally, at least, let's finally get at least an outline of a full setup of de Rham theory. So let's do the general setup. Of de Rham theory in Rn, and thus in our for submanifolds as well. So what are K-forms? K-forms are smooth assignments to to K vector fields spit out a function that is, they evaluate at each point. And the evaluation is smooth when the vector field is that you feed it is smooth. And these are linear in each variable. So if I scalar multiply all the x coordinates of in my vector field, I'm gonna the form will spit out something that just is scalar multiplied. And anti-symmetric or alternating are two words. That means if I just swap two vector fields, say they're next to each other on the list for simplicity, I'll introduce a minus sign. So, and then the universal example is that which we'll call dx1 wedge or dxi1 wedge, dxi2 wedge, etc. And I'll call this often dxi for short. And I've got k of these because this is a k form. And this is, I can take this as a definition up to sine, project onto the span of the corresponding unit vectors, and take k-dimensional volume. Okay. And those are universal examples because the theorem is that any K form, and this is a theorem, is equal to the sum of these dxi with, of course, quote unquote, scalar multiplication, scalar function multiplication, which means at every point, scalar multiplication. Great. So we've been talking about these. This is pretty close to the definition from last time. But to set up the theory, there's two key players, two key structures. There's an exterior derivative, and there's a wedge product. Notice that both of these are part of our universal example. And so part of the setting up this theory is that the definitions we're about to be giving are consistent with this universal example. So let's do exterior product first. At a point, and we often do this, and then there's some smoothness to check for this construction. And again, we won't bother in a quick crash course like this. If I have a K form omega and an L form tau, then omega wedge tau is going to be a K plus L form. So it's got to take K plus L vectors and spit out a number. And it's going to be the sum over shuffles of my indices of omega evaluated on, I'm going to evaluate it on a subset of the vectors. They're going to come in order. So shuffles are, I'm shuffling the first K and the last L things. So notice that V1 is less than V2 is less than VL, and I'm going to keep that ordering through the shuffle. It's like when you shuffle two decks of cards, they're shuffle a deck of cards using two halves. Each half retains its order. And there's going to be signs of these shuffles. And then I'm just going to let omega and tau do their thing. That is, evaluate on those shuffled sets of vectors. Okay. So an example, if omega and tau are one forms, then what we get is the formula is just omega wedge tau of V1, V2 equals omega V1 tau V2 minus tau of V1 omega of V2. And let's do an example of that. In R2, dx wedge dy, so dx is this one form that projects onto the x-axis, dy projects onto the y-axis, takes the length evaluated on two vectors, let's call them A, B, and C, D, I claim is going to be A, D minus B, C. So that's an exercise, say. So these forms have something to do with determinants, which makes sense if you're talking about area, signed area is given by determinants. And these forms are given by determinants. And the wedge product is a way to sort of take a k-dimensional determinant and an l-dimensional determinant and produce a k plus l dimensional determinant. So, but it's sort of, this example makes it sort of seem easy. This is happening in ways where I could also be projecting on any number of spaces. It's arbitrary sort of Grossman geometry. So further exercise is to evaluate dx, wedge dy, wedge dz on three vectors. The thing there is even at least even seeing why associativity holds and how it works in this example is interesting. So there's a lot going on. You make these definitions and then you often have, and they seem simple enough, but you want to establish properties and you have to work a bit harder. Okay. More of a convention, well, it's part of the definition. Functions are zero forms. And f wedge omega is often shortened to f omega, like f dx. So the scalar multiplication of a form by a function is something that's covered here. And so an exercise, by the way, is show our check compatibility of this definition with the above. I made one definition of dx sub capital I up here with wedge products, but I didn't define wedge product. Now I'm defining wedge product, and I want to say that you get the same answer whether you project and take volume or whether you use the wedge product. Okay. So that's wedge product or exterior product. Then the other key piece of structure is if f is a function, I've got this exterior derivative, and it really is just the derivative. Look, we're going to take the partial, if I'm working in coordinates, I get this one form. Basically, it's the gradient, right? This is the gradient, but in our name of forms. But or equivalently, it is the one form whose value on some vector v, vector field v, is the directional derivative of f in the direction of v. So this is really clever. This is saying that the derivative, we're normally used to thinking of the derivative as a vector field, but honestly, through the gradient, and again, it's great to think about gradients sometimes, but honestly, if the derivative is really supposed to be, well, when we dot with the gradient, it's really supposed to tell you in some direction what is the rate of change. And what you're saying is, given a function and a vector or a vector field, I can spit out a number, or in the vector field case, I've got a new function, right, which is telling me how I'm moving in those directions. That's what a one form does. A one form is going to take a vector field and spit out a number at every point, or spit out a function. So the derivative of a function is more naturally a one form. So let's just the first example or 0th example is if f in 3 variables x, y, z equals x, then df is our friend dx. But this could now be defined in the second way, and this again is a way to go back and make kind of more elegant definitions for what forms are. You can just start with this notion of exterior product and wedge, and you get everything. So in other words, here again, dx equals dx. So we extend to all forms by the Leibniz rule. And what is that? That says that d of a wedge, and that could include d of a function times a form, because that's a 0 form wedge of form, equals d of the first wedge the second plus -1 to the degree of the first. That's just the number of, well, one forms, two forms, that's the k in our definition, omega wedge d tau. And then theorem, and again, proof is an exercise. Sorry, I'm having internet issues for a second. Maybe I'll go with this. D of D of any form is 0. In other words, we often say this is d squared equals 0. Okay, hopefully this is okay. So that's remarkable. Let's just give little examples first, not of the theorem, but let's just take d of something simple like x squared plus y dx and 1 over x plus y dy. And let's see how these two pieces of the definition. So we should really think of this as definition part 1 and definition part 2 here. These two pieces of the definition play together. So this is equal to, well, I've got to take I'm going to think of that x squared plus y dx as a 0 form times a 1 form. So I'm going to take d of x squared plus y, and that's 2x dx plus dy. And I'm going to wedge that with dx. And then I also have to take x squared plus y times d dx, and that's 0, because d squared is 0. And then I have to take the derivative on the second, and I get minus 1 over x plus y squared dx, x plus y quantity squared. I can do single variable calculus. And I would get the same thing for dy. So let's just, and that is going to be wedge dy plus, and then I'm going to get a 0 term. And so then I have to expand these, and I get 2x dx wedge dx. And another fact is that because the wedge product is antisymmetric, and you know what? I think I did not state that. So let's state that important theorem. Omega wedge tau equals minus 1 to the degree of omega times the degree of tau wedge omega. So if I've got two odd forms, they anti-commute. Two even forms will commute. But so dx is an odd form, and so dx wedge dx will be minus dx wedge dx, and so that's 0. And then I've got plus 2 dy wedge dx. And then I've got the term below, I've got minus 1 over x plus y quantity squared dx wedge dy. And then I'm going to have a 0 term and another 0 term from above. And so that in the end, and now I want to collect terms, I've got a dy wedge dx and a dx wedge dy. So I'm going to change the order of multiplication again. Again, that's a minus sign because I've got two 1 forms. And finally, I get minus 2 minus 1 over quantity x plus y squared dx wedge dy. Okay. Phew. So let me give another exercise to revisit, because I basically gave this as an exercise last time, but we didn't have everything in front of us. Again, I can take functions, I take gradient, I get a vector field. And of course, I've got del, del cross, del dot. I've got 0 forms, 1 forms, 2 forms, and 3 forms. This is an R3. And I claim that there are isomorphisms here so that all of these classical operations on vector fields become our D. And our D was defined sort of elegantly through, there's really just the gradient, and everything else is determined by the Leibniz rule, and thus this exterior operator. And that's remarkable. This is one of those things where in math we often, some people kind of debate, is it discovered or created? This definitely feels like it's discovered. The fact that vector calculus can be deduced by such a small amount of data, namely this wedge product and this D, on the key structures of differential form. So just the definition of differential form, wedge product, and D gives us a full theory of calculus, and again, a Stokes theorem, which I won't prove for you, by the way. Definitely not. That's a highlight in it's not a crash course. It comes down to the fundamental theorem of calculus once you get all your definitions right. So, yeah. So some terminology, the zero forms on R3 we call omega 0 R3, and the one forms omega 1 R3. The two forms omega 2, and sometimes we put dr for de Rham. And we've got this D, or more generally, let me erase now. If I look at some manifold M, and it can keep going, this is called the de Rham complex. So this is this fundamental object that that connects, that lets us do calculus on manifolds, a particular kind of calculus with linear, multilinear forms on manifolds, and it also, as I stated for that theorem that sort of was this, following Green's theorem in the plane, it also is a measure of the topology of the manifold. So it simultaneously is a place where calculus happens, and that calculus measures the topology. And again, all we're going to do for Rn especially, we just start with functions, and then take exterior derivative and wedge product, and we get all this structure. So in formulas, a lot of these things can be really complicated, but conceptually, there aren't too many basic tools around. You've got the functions on the manifold are your background. You've got exterior derivative gives you one form. You've got wedge product, and those are ways to kind of measure arc length, not arc lengths, but measure some quantities unlike arc lengths along curves. And then you've got wedge products to there's these sort of determinants that sort of then give you two-dimensional, three-dimensional, and higher dimensional volumes, but you can derive them all from those. Okay, so let me just say what we're gonna do next time, and then have one last small topic. Next time, we're going to get in the meat of a lot of key topics. We're going to talk about degree of a map between manifolds. We're going to talk about Gauss's integral for linking number. And we're going to get around to the integral that comes up in some types of studies of magnetism, this Whitehead integral for the Hopf invariant. So hopefully we'll get there next time. Let me, one additional thing that'll be useful as we're doing that, both technically useful and I think conceptually useful, are tone forms. And I really think of these as complementary. They're forms, but let's go back to my favorite example, d theta. And what d theta is doing is, if I've got a curve C, I'm the integral of along C of d theta is just telling me how much progress I'm making, or dx even is just telling me how much progress I'm making left to right. Okay, so and that's constant. If that were sort of a real world thing that's being implemented, I would put and the curve is where something is driving, I would put a GPS in it, and I would sort of measure constantly. And, as you go along, whatever your progress is in the theta variable, that's the toll you're going to pay. There's an alternate way to collect tolls, the classical way, pre-GPS. Well, this is still relevant, right? Often this principle is still used rather than, I don't think anybody has a continuous use via GPS. That's not politically viable. But what you do is you've got some sort of bump function. I'm just going to call this f d theta. And I'm going to think of f is a function. This is going to be a function in theta and r, but it's really just a function in theta. It's going to be uniform across r. And what it's going to do is the graph of f on the circle, it's going to be like a Dirac-ish function. It's going to be 0 outside some small neighborhood of the unit vector pointing right, E1. And then around there, I want a total integral of f to be 1, but I want it to be supported in a point. And this f d theta, if I integrate and I don't cross the axis or you come close to the axis, it's going to be 0. But as I cross the axis, it's going to integrate to 1. And the point is that that for closed curves, I get the same answer. And we'll talk about this a little bit. So integral over c d theta is integral over c f d theta. So I can, or up to, well, 1 over 2 pi as I've written it, because I just said that this integral over f should be 1. Maybe I should have said it should be 2 pi, and then I wouldn't have had to fudge that. But the point is that these are equivalent ways. If I know that all trips are going to begin and end at the same place, and I'm in R2 minus 0, I can sort of account for this widening number, take this toll either by continuously taking a toll as you make any progress in the theta direction, or just I'm only going to focus on crossings of the x-axis, and when you fully come across, that'll be $1, and we'll collect it however many times you wind around. So this is a tome form, and the thing about it is, of course, I could have collected it anywhere. I could also collect it, out in this crossing here, and maybe you see where I'm going. I could be collecting it, and of course, I would need to collect less as I go along. Each one is going to give the same value on a closed curve. And eventually I could approximate my original d theta, which seems odd, but the point is that for various things, you can get some mileage for your intuition by reasoning in terms of these tome forms. Because again, if I take a sum of tome forms over sufficiently many of these submanifolds or whatever, I can approximate my original nice smooth forms. In some cases, tome forms are just better to think about, but in any case, they will give us a way to reason about forms geometrically through these subspaces. It's interesting, actually, piece of my own research very recently, just posted to the archive in this past year, is allowing us to do this not over R with calculus, but do it over the integers. Just consider these kinds of submanifolds. Remarkably, despite topology being in existence for about 120 years, that theory hadn't been fully worked out until my co-authors and I did last year. So that's also to say that I really love tone forms. I love to think in those terms, and we'll use those as we to get some further intuition as we think about degree, Gauss integral, and Whitehead integral.